why are some carbocations more stable than others? Stay tuned. I'm going to give you 2 different ways to look at the problem to figure this out. Hey there, OChemNinjas. As we move throughout organic chemistry, we're going to encounter a lot of carbocations. But not all carbocations are made the same. Some are more stable and some are less stable. When we see a carbocation, the first thing we need to do is label it by its degree of substitution. We look at the carbocation carbon, and we count up the number of other carbons to which that carbocation carbon is attached. This carbocation is attached to 3 other carbons, so we call this a tertiary carbocation. Not third-degree carbocation. Tertiary carbocation. When the carbocation carbon is attached to 2 other carbons, this is a secondary carbocation. Not 2-degree. Attached to 1 other carbon is primary, and no other carbons is a methyl carbocation. So what is the stability trend for carbocations? Tertiary carbocations are more stable than secondary carbocations. Secondary carbocations, in turn, are much more stable than primary carbocations. And primary carbocations are themselves much more stable than methyl carbocations. But why? Let me give you 2 different explanations that can help explain this stability trend. The first way to think about it is alkyl groups are electron-donating groups. They can modulate the amount of electron density in the molecule as an electron-donating group. If you're not familiar with the concept of modulating electron density or electron donating and electron withdrawing groups, I have a refresher video that I'll link to down below. But alkyl groups are electron donating. The carbocation carbon is positive because it lacks electron density. It's missing electron. If it lacks electron density and the alkyl groups are electron donating, they're pushing more electron density towards that positive charge, diminishing the effect of that positive charge. Anything to make that positive charge more stable will make the whole molecule more stable. And a tertiary carbocation has 3 electron donating alkyl groups, helping that carbocation be more stable. 3 of these electron donating groups is better than 2 electron donating groups. The secondary carbocation is still fairly stable, but it only has 2 electron donating alkyl groups, which is less stable than the 3 electron donating groups in the tertiary carbocation. The primary carbocation only has the 1 alkyl group, and the methyl carbocation does not have any electron donating alkyl groups, and it is the least stable carbocation. The second way to look at this is through a new term called hyperconjugation. Hyperconjugation is a stabilizing effect of neighboring sigma bonds donating some of their electrons to neighboring empty orbitals. That was a mouthful. The best way to picture this is through pictures. So let's look at the orbital diagrams for each of these carbocations. Pause the video, see if you can figure out the hybridization of the carbocation carbon, its geometry, its bond angles, and what orbitals comprise this atom. And think about what that orbital picture would look like. Sketch it out if you're able to. I'm going to draw the orbital picture here, so really pause the video because in a second everything's going to flash and all the orbital drawings are going to be drawn out for you. These are the molecular orbital pictures for these carbocations. What I want you to see is that this plane has been tilted so it's coming in and out of the plane of the board with some things sticking up above and some things sticking below. If you've never seen these types of drawings or would like a refresher on how to draw molecular orbital pictures, I have a video that I'll link to in the description below. I want to draw your attention to the carbocation carbon. It is sp2 hybridized, trigonal planar, with an unhybridized p orbital perpendicular to that trigonal plane. And that unhybridized p orbital is empty. That's where the positive charge lives. That positive charge empty orbital is very unstable. Anything we can do to give some electrons back to that positive charge would help make the whole molecule more stable. And that's where hyperconjugation comes in. What I want you to notice is on the neighboring carbon, one of the carbon-hydrogen bonds can rotate to being almost essentially parallel to the empty p orbital. And when that happens, the electrons in this sigma bond can lean over slightly and share some of their electron density with the empty p orbital. Sharing some of that electron density diminishes the positive charge and makes the whole molecule more stable. And the cool thing with the tertiary carbocation is there are 3 of these essentially parallel sigma bonds that can donate some of their electron density to the empty p orbital. With triple hyperconjugation, the tertiary carbocation is the most stable of these carbocations. The secondary is not looking too bad either. It has 2 of these parallel sigma bonds that can donate some of their electron density to the empty p orbital, making the secondary carbocation not quite as stable as the tertiary carbocation, but still fairly stable. Notice that the primary carbocation only has 1 of these adjacent parallel sigma bonds that allows for donation of electron density. The primary carbocation is only stabilized by 1 instance of hyperconjugation, so it is not nearly as stable as the secondary or tertiary. And the poor methyl carbocation has no hyperconjugation available to it. It is exceedingly unstable and really never forms in organic chemistry. So these are 2 ways we can rationalize carbocation stability trend. The electron-donating alkyl groups make the carbocation more stable, and the way they do that is through hyperconjugation, the leaning over of this electron density from the parallel adjacent sigma bond that allows the positive charge to be more stable, which makes the whole molecule more stable. As an added bonus, sometimes that neighboring bond leans over so far that it falls over and it actually shifts the entire carbon-hydrogen bond over to the next carbon. That's called carbocation rearrangement, and I have a separate video that I'll link to below about that. There is one other factor that affects carbocation stability, and that's resonance. If I can stabilize a positive charge by resonance, that makes the entire carbocation much more stable than we'd otherwise expect. Even though this is technically a primary carbocation, because it is stabilized by resonance, it's about as stable as a tertiary carbocation. Resonance really helps stabilize carbocation. What about you? Have you thought about hyperconjugation this way before? Leave me a comment below.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.